Okay, so hello and welcome back. So in the previous 8 videos we talked about, basically we did a review on probability class 9 and class 10, and what we want to basically start here is probability class 11, which is chapter 16 of class 11. Now what we did in this book here was basically empirical probability. So empirical probability or experimental probability, I think it was experimental probability, as experimental probability is basically involves doing experiments, meaning that, for example, you throw a dice or you toss a coin or you do some sort of experiment, something like that, for a large number of times. So for example, you throw dice for 100 times, 200 times, 300 times, 1,000 times, 5,000 times, and then you record the outcomes of the experiment in a table, and then based on the number of, for example, suppose that, for example, you get, for example, I don't know, for example, 1,000 ones, and you have for example thrown the dice for a total number of 6,000 times in total, and then you've got basically 1,000 ones. So to calculate the empirical probability of getting a 1, you divide the number of times that you actually got the 1, which is 1,000 times, and you divide that by the total number of times that you throw the dice, which is 6,000 times, and that gives you 1/6. That's the empirical probability of getting a 1 in the experiment of throwing a dice. Okay, so that's basically all that there is to empirical probability. Now in the next chapter, which was basically this one, which was probability class 10, that we did the review, what we said that was that basically the more that increased the total number of times that we threw the dice, the probability of, for example, getting a 1 was getting closer and closer and closer to 1/6. But if you do it, for example, for 100 times or 200 times, you're not going to get a 1/6. That's going to be a number much smaller than 1/6, even 1/2 of 1/6. For example, something like 2/6 or something like that, which is equal to 1/3. And then slowly your numbers will tend towards basically this number, which is 1/6. But of course, that's provided that you throw the dice for example, 10,000 times or 20,000 times, and so on and so forth. So then we said that for the kind of experiments where we are ready to basically make some assumptions, then we don't actually need to throw the dice for that high number of times. We can just simply calculate the theoretical probability of throwing a dice, which doesn't involve doing any sort of experiment, and that is basically when you, for example, when you want to calculate, for example, the probability of, for example, a spacecraft, for example, going into the space, for example, when such and such things happen, we want to calculate the probability of a certain thing happening in a spacecraft, for example, in the experiment that the spacecraft, for example, leaves the Earth and at a certain stage goes to some other certain stage and something like that. So this is the sort of experiment which is not which is not easy to repeat, meaning that if you want to basically to launch a spacecraft, it costs a lot of money, so you cannot repeat that experiment, and I mean in most cases not even once. So you have to find some way to calculate the probability, and for that we use the concept of theoretical probability. Now we said that over here we have to make some assumptions, otherwise we cannot actually do the calculation. And the assumptions that we had to make was that for example, in the case of tossing a coin, suppose that you want to calculate the theoretical probability in the case of tossing a coin. And so here we have to make some assumptions. So we assume that, for example, that the coin is fair. And what that means is that, for example, it is basically symmetrical, so that there is no reason for it to come down more often on one side than on the other side. That means that the coin is fair, for example. And this basically, we call this property of the coin, we call it being unbiased. Meaning that it's not biased towards basically heads or tails. There is no bias in the for example, due to the symmetry. I mean, there could exist as a condition in the coin, or in that, for example, in that particular coin that you're flipping or tossing, that, for example, because of some problem with the symmetry of the coin, that the coin is more biased towards, for example, heads than tails. So you don't want that to exist, because that would basically ruin the results of your experiment. So you want the coin to be fair, and that means that the coin is unbiased. And of course, it's supposed to be a random toss, for example. It's supposed to be a random toss, meaning that you let the coin basically land on whatever surface, for example, it is that you're using, on which basically the coin is supposed to land. The coin is supposed to, for example, land freely without any bias or without any interference on your part. So, and then one more assumption that we need to make is that basically all the possible outcomes of this experiment are equally likely to occur. All the possible outcomes of the experiment are equally likely to occur. And what that means is that let me give myself some space here. And what that means is that, for example, as an example, suppose that we throw a dice. So first of all, the dice has to be a fair dice, meaning that it's not biased towards any of the numbers. And the possible outcomes are 1, 2, 3, 4, 5, and 6. Now, each number has the same possibility of showing up. So that means that the equally likely outcomes of throwing the dice, or a dice, so then you can say that the equally possible outcomes, the equally likely outcomes of throwing a dice are, you can say that are basically 1, 2, 3, 4, 5, and 6. Now, as an example, of course, not every experiment has equally likely outcomes. For example, suppose that, for example, you have a bag we gave this example of the bag. For example, you have 4 red balls. You have 4 red balls in the bag, and you have, for example, 1 blue ball. You have 1 blue ball here. So if you draw a ball from this bag, these 5 balls are in a bag, and you cannot see inside the bag. So you're supposed to just draw, without looking into the bag, you're supposed to draw a ball at random. So when you do this experiment, of course you would agree that you would be more likely to draw a red ball than a blue ball, because there is simply more red balls in the bag. So you're more likely to get a red ball than a blue ball. So this experiment over here does not have equally likely outcomes. Or basically you can say that the outcomes being the red ball and the blue ball are not equally likely. But for example, if you think about the outcome of for example drawing a ball, where basically the color is not important anymore, drawing a ball from the bag, in that case, then all the possible outcomes of the experiment would be equally likely. So then basically, in order to be able to calculate theoretical probability, we had to make the assumption that all the experiments have equally likely outcomes, meaning that all the experiments have equally likely outcomes. Right? All the experiments that basically that we study using the concept of theoretical probability, they have equally likely outcomes. Meaning that what happens if the experiment does not have equally likely outcomes. So let's take the example of this bag over here. So suppose that you want to, for example, calculate the probability of getting a red ball. Calculating the probability of drawing a red ball. of drawing a red bar. So we said that basically we define P of E. We define P of E as basically number of outcomes favorable to E, number of outcomes favorable to E divided by the number of all possible outcomes of the experiment. Number of all possible outcomes of the experiment. All the possible outcomes of the experiment. Now, for example, the number of outcomes favorable to E would be, now suppose that I'm drawing a bar and I'm calculating the probability of drawing a red bar. So that would be basically 4, meaning that any of these 4 balls, if I draw any of these 4 balls, that would be the number of outcomes favorable to E. So that I would calculate that I would take that as 4, and then the number of all possible outcomes of the experiment would be basically 5, because I have 5 balls over here. Although this example here is not a very good example to show the concept here, the concept of basically this assumption that we had to make. We had to make this assumption that basically all the experiments have equally likely outcomes. That we will understand in the chapter that we are covering right now. So now that's basically an overview of what we did in the previous 8 videos. So now let's go and the first thing that we need to understand is basically what this assumption actually meant. The assumption that all the experiments have equally likely outcomes, or at least the experiments that we used, basically the experiments that we studied using this method, which was theoretical probability. So now let's see what we have here. So as an introduction, we said that in earlier classes we studied about the concept of probability as a measure of uncertainty of various phenomena. We have obtained the probability of getting an even number in throwing a dice, as for example 3/6 or 1/2. Here the total possible outcomes are 1, 2, 3, 4, 5, and 6, and the outcomes in favor of the event of getting an even number are 2, 4, and 6. That is 3 in number. In general, to obtain the probability of an event, we find the ratio of the number of outcomes favorable to the event to the total number of equally likely outcomes. So this theory, I got the point. Okay, this theory of probability is known as classical theory of probability. So what that means is that, for example, in the probability of getting an even number in throwing a dice. Let's talk about the probability of getting an even number in the experiment of throwing throwing a dice. So you want to get basically getting an even number. So the event that we have is basically, call it E. It's the event of getting an even number. So all the possible outcomes of the experiment are basically 1, 2, 3, 4, 5, and 6. So out of these numbers, basically you know that this number, and this number are even numbers, 4 and 6. So these three numbers are even numbers. Now the probability of event E happening would be the event of getting an even number, which is basically the number of outcomes favoring that event, which is basically 1, 2, and 3. So you have 3 outcomes favoring this event, and you divide that by the total number of the outcomes of the experiment, which is 1, 2, 3, 4, 5, 6. 6 by 6, I mean the number of these numbers, not just 1 through 6 or anything like that. So so that gives me basically 1/2, right? That gives me 1/2. Now it says that here in general, to obtain the probability of an event, to obtain the probability of an event, we find the ratio of the number of outcomes favorable to that event. We find the ratio of the number of outcomes favorable to that event, to the total number of equally likely outcomes, to the total number of, equally likely outcomes. So the equally likely outcomes here, what it means, which we didn't understand back there, is that basically, so it says that in general, to obtain the probability of an event, we find the ratio of the number of outcomes favorable to that event. So basically you can write P of E is equal to the number of outcomes favorable to E, and then you divide that to the total number of equally likely outcomes. likely outcomes. So what that means is that equally likely outcomes here basically refers to the experiment of for example, let's say that you have basically four red balls and one blue ball in a bag, and you draw one ball at random. Now, to calculate the probability, so let's say that the event E is basically the event that the ball is red. So then the probability of E, to calculate that, we said that we basically calculate the number of outcomes favorable to E, which is clearly 4 here. You have 4 balls here. So we calculate the number of outcomes favorable to the event, which is 4, divided by the total number of equally outcomes, which is equal to 5. 4 plus 1 is equal to 5, because drawing a ball from the bag can be thought of as equally likely outcomes, because you are equally likely to draw any ball from that bag, right? And so that the assumption that we had to make that over here, that we didn't understand it, that we said that basically all the experiments have equally likely outcomes. That's the meaning of that. Otherwise, for example, if we were talking about some experiment in which, for example, drawing a ball from the bag did not have basically equally likely outcomes, of course you couldn't use this formula and this whole method over here in order to find the probability of that event happening. So that's basically one thing that we cleared here. So this theory of probability is known as classical theory of probability or theoretical probability. Now, in class 9, we learned to find the probability on the basis of observations and collected data. This is called the statistical approach of probability. So, where we had basically over there we called it the experimental or empirical probability. So that has been called here the statistical approach of probability. This has been called here basically a statistical approach of probability. A statistical approach of probability. Of course, because it does involve a lot of statistics, you have to take all of your numbers, put them together using all the concepts of statistics. So that has been called the statistical approach of probability. And then we had something else which we did in the last chapter that we did here, that was basically which we called theoretical probability, that has been called the classical theory of probability. Classical theory of probability. probability. Okay. Now both the theories have some serious difficulties. For instance, these theories cannot be applied to the activities or experiments which have infinite number of outcomes. Of course, we did use this one for a couple of cases, but we will see what they mean by this. It says that, for instance, these theories cannot be applied to the activities or experiments which have infinite number of outcomes. In classical theory, which is basically this one, the theoretical probability, in classical theory we assume all the outcomes to be equally likely. Recall that the outcomes are called equally likely when we have no reason to believe that one is more likely to occur than the other. In other words, we assume that all outcomes have equal chance or probability to occur. Thus, to define probability, we used equally likely or equally probable outcomes, which is of course not the case all the time. Most of the time it's not the case, because, for example, suppose that you have a bag of marbles. This bag of marbles, it's like a bean chair. It's like a bean chair, it's like a big container of marbles. There is this is full of marbles, like I don't know, 15,000, 20,000 marbles in this big container. And in order to basically use theoretical probability of getting, suppose that, for example, there is 200 red balls here, there is, for example, 500, for example, yellow balls here, and there is, for example, 1,800, for example, purple balls in here, and so on and so forth. Now all of these are mixed together, right? All of these are mixed together. Now if I told you now, and suppose that there was no way to get to the bottom of the, and all of these basically you have, for example, 9 colors of balls all mixed up together in this big container, like, for example, it's like a cube of, for example, something like this. It's like a cube of some cube like this, and for example this is for example 5 meters, this is 5 meters, and this is, I don't know, 3 meters, for example, or so. And there is no way for you to get inside the cube unless you started from basically from the top of the cube, meaning that at any time, if you wanted to pick a marble from this cube, if I were to calculate, for example, the probability of getting, for example, a red marble, that would be, for example, 200 divided by, for example, the total number of marbles in this container, which, let's say, that's 15,000 marbles in this container. Of course, it would be much more than that given these dimensions, but let's go with these numbers. But the problem with this, for example, with this problem, to solve this problem, the problem is that basically, well, of course, you could argue that the marbles that are placed on top, they are equally likely outcomes of the experiment. But suppose that there is a marble over here, down here, which is right at the bottom of the cube, and there is no way for you to get there unless you picked all of these marbles on the top, and then you could get down here. So then, of course, in this case, you could not say that all of these marbles have, drawing a marble is cannot be considered as an equally likely outcome, although theoretically in solving the problems we would say that, for example, that is basically an equally likely outcome of the experiment. So for these kinds of problems we need different approaches to solve the problem, and here basically it says that recall that the outcomes are called equally likely when we have no reason to believe that one is more likely to occur than the other. In other words, we assume that all outcomes have equal chance or probability to occur. In other words, we assume that all outcomes have equal chance or probability to occur. That's the assumption that we make. Thus, to define probability, we use the equally likely or equally probable outcomes. This is logically not a correct definition. Thus, another theory of probability was developed by A.N. Kolmogorov, a Russian mathematician, in 1933. So now this Russian mathematician, basically his name is A.N. Kolmogorov. In 1933 he developed basically another theory of probability, and what that was, he laid down some axioms to interpret probability in his book Foundation of Probability. He wrote a book called Foundation of Probability. And published that in 1933. So in this chapter we will study about this approach called Axiomatic Approach of Probability. So it seems that the approach that he developed there is called Axiomatic Approach to Probability. Axiomatic Approach to Probability. And that's basically what we want to do in this chapter. Now, to understand this approach, we must know about few basic terms, like, for example, random experiment, or sample space, or events or sample events, and some other terms. So let's get started with this and let's see what we have basically in this chapter. Okay, so now let's see what random experiments are. So basically, random experiments says that in our day-to-day life we perform many activities which have a fixed result no matter any number of times they are repeated. For example, given any triangle, without knowing the three angles, we can definitely say that the sum of the measures of the angles is 180 degrees. Or we also perform many experimental activities where the results may not be the same when they are repeated under identical conditions. for example, when a coin is tossed, it may turn up as heads or tails, but we are not sure which one of these results will actually be obtained. Such experiments are called random experiments. So, of course, this is not a real definition, but it says that we perform many experimental activities where the results may not be the same when they are repeated under identical conditions. For example, when a coin is tossed, it may turn up as heads or tails, but we are not sure which one of these results will actually be obtained. So such experiments are called random experiments, meaning that, for example, let me close the window. So basically, for example, tossing a coin would be an example of a random experiment, because when you toss the coin, you don't know whether you're going to get heads or tails. That's based on what we read here is basically a random experiment. So an experiment is called a random experiment if it satisfies the following two conditions. It has more than one possible outcome, so then you can say that this looks more like a definition. So an experiment is called a random experiment. Is called a random experiment if it satisfies the following two conditions. If it satisfies the following two conditions. So number one, it has more than one possible outcome. It has more than one possible outcome, and also it is not possible to predict the outcome in advance. It is not possible to predict the outcome in advance. So, for example, check whether the experiment of tossing a dice is random or not. Of course, it's random because it has more than one possible outcome. You get 1 through 6 as the possible outcomes, and it's not possible to predict which one, to predict the outcome in advance. It's of course a random experiment. In this chapter, we shall refer to random experiment by experiment only unless stated otherwise. So from now on, if we say experiment, what we mean is when we use the word experiment, what we mean is actually a random experiment. A random experiment. Unless stated otherwise. Now, there is something called outcomes and sample space. So a possible result of a random experiment is called its outcome. Well, of course, that's what we already know. A possible result of a random experiment is called its outcome. Consider the experiment of rolling a dice. So the outcomes of this experiment are 1, 2, 3, 4, 5, or 6 if you are interested in the number of dots on the upper face of the dice. The set of outcomes would be the set of outcomes, if you roll a dice or if you throw a dice, the set of outcomes would be basically 1, 2, 3, 4, 5, and 6. It is called the sample space of the experiment. This is called the sample space of the experiment. The sample space associated with the experiment. Sample space is denoted by the symbol S. So then you can say that, for example, S, or the sample space associated with this experiment, is 1, 2, 3, 4, 5, and 6. In other words, each outcome of the... Okay, and then we have each element of the sample space is called the sample point. Each element of the sample space is called a sample point. In other words, each outcome of the random experiment is called a sample point. Or you can say that, or you can also say that each outcome of a random experiment is called a sample point. It's called a sample point. Okay. Now let's take basically two examples here. Example number 1. 2 coins, a 1 rupee coin and a 2 rupees coin, consider two coins of two different denominations, are tossed once. Find the sample space. So what that means is that they are tossed simultaneously. So two coins are tossed simultaneously of course the coins are of different denominations. Now find the sample space. You want to find the sample space. Now, as a solution, it says that clearly the coins are distinguishable in the sense that we can speak of the first coin and the second coin. So, since either coin can turn up heads or tails, the possible outcomes may be basically you can imagine that you have the first coin and the second coin. The two different outcomes for this coin would be heads and tails. The two different outcomes for this coin would be the same thing, heads and tails. So then, if you have heads on both coins, you would get basically heads and heads. If you get basically, you could get basically heads on the first coin, tails on the second coin. You could get tails on the first coin, heads on the second coin, and you can get basically tails on both coins. So then thus the sample space is going to be S is equal to basically this set. Now the outcomes of this experiment of ordered pairs of H and T. For the sake of simplicity, the commas are omitted from the from the ordered pairs. Okay. Example number 2, we have find the sample space associated with the experiment of rolling a pair of dice. One is blue and the other one is red, and they are basically they are thrown once. Also find the number of elements of this sample space. So you have two dice basically. You have 2 dice, red and blue. Red and blue. Now you throw these 2 dice together simultaneously. So you want to find the sample space. So then of course it's the same problem as basically the same problem that we had before, meaning that you could get, for example, you could have some table like this, right? So you have basically here you have, for example, your red dice, here you have your blue dice. One, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6 here. And then if I so to find the sample space, if this is your red dice, this is your blue dice, the outcomes of this, of throwing this dice you could get a 1, you could get a 2, 3, 4, 5, and 6. The same thing, the red one, 1, 2, 3, 4, 5, and 6. And then you would get 1, 1 here, 1, 2, 1, 3, and so on and so forth, and so on and so forth, and so on and so forth. So that all of these 36, 6 times 6, 36 elements would be the sample space, this in a set, of course, the sample space of this experiment. So the solution says that suppose 1 appears on the blue dice and 2 on the red dice. We denote this outcome by an ordered pair 1, 2. Similarly, 3 appears on the blue dice and 5 on the red dice. The outcome is denoted by 3, 5. In general, each outcome can be denoted by the ordered pair x, y, where x is the number appearing on the blue dice, for example, and this on the red dice. Therefore, the sample space is given by, you could write it as S is equal to the set of ordered pairs x and y, such that, you can write such that this way, or this way, such that x is the number on the blue dice, x is the number on the blue dice, and y is the number on the red dice. And the number of elements of this sample space is 6 times 6 is equal to 36 elements, and the sample space is given here. You can of course keep writing these elements as, for example, S is equal to, for example, 1, 1, 1, 2, 1, 3, all the way up to, for example, 6, 6. And you would have basically 36 elements here. And that's basically the whole story. Now, as another example, we don't have much material here to cover. we can do this one and then we get some exercises to do. Okay. Okay, so the next question that we have is in each of the following experiments specify appropriate sample space. So for example, a boy has a 1 rupee coin, a 2 rupee coin, and a 5 rupee coin in his pocket. So you have basically 3 different coins. You have 3 different coins in your pocket, 1, 2, and 5 rupee coin. He takes out 2 coins out of his pocket, one after the other. And basically, he takes out basically 2 coins. 2 coins, one after the other. One after the other. So now the sample space for this experiment would be that okay, so let's see how we can think about this. The solution is let Q denote a 1 rupee coin. Denote the 1 rupee coin. And H denote the 2 rupee coin. H denote the 2 rupee coin. And R denote the 5 rupee coin. So the first coin he takes out of his pocket may be any of the 3 coins, Q, H, and R. Corresponding to Q, the second draw may be H or R. So the result of 2 draws may be basically Q and H and Q R. Similarly, corresponding to H, the second draw may be Q or R. Therefore, the outcomes may be H and Q, H and R. Lastly, corresponding to R, the second draw may be H and Q, so the outcomes may be R, H, and RQ. Okay, so basically, if you take the 1 rupee coin out first, basically the outcomes might be, meaning that first you take so corresponding to Q, for example, the second draw may be H or R. So it might be QH or QR. Okay. Not a good way of thinking about it, but anyway, it's good enough. So if you draw the first coin, if you take it as H, for example, supposing that you take the 1 rupee coin out first, you would after that you could have QH, or you could draw H, or you could draw R. So the results of 2 draws may be QH or QR. So you could take the second one could be H, or the second one could be R. So it would be Q and then H. It could be Q and then R. Okay. If you take the H out first, basically the next coin that you could take out could be Q or could be R. So it would be H, Q or HR. And if you take the first one that you take out is R, the next one could be H or it could be Q. So RH and RQ. So then the sample space. Which is equal to S, would be basically QH, it would be QR, it would be HQ, it would be HR, it would be RH, or it would be RQ. That is your sample space. Or the second problem that we had here is basically a person is noting down the number of accidents along a busy highway during a year. So a person is noting down the number of accidents along a busy highway during a year. So then the sample space would be I don't know, suppose that for example the number of accidents along a busy highway during a year of observation can be either 0 for no accidents, or 1 or 2 or some other positive integer. Thus, a sample space associated with this experiment is S is equal to 0, 1, 2, and so on and so forth. Could be any number. Okay. Now, example number 4 is a coin is tossed. If it shows heads, we draw a ball from a bag consisting of 3 blue and 4 white balls. If it shows tails, we throw a dice. Describe the sample space of this experiment. So a coin is tossed, and when the coin is tossed, if it shows, so you toss the coin, if it shows heads, it could show heads or tails. If it shows heads, we draw a ball from a bag. From a bag consisting of 3 blue and 4 white balls. Draw a ball, 3 blue and 4 white balls. Right? And if it shows tails, we throw a dice. And then we throw a dice. Okay? Describe the sample space of this experiment. So here we need to basically denote different things with different letters, meaning that, for example, heads and tails, you can already denote them by heads and tails. Now, these you could denote with, for example, blue, for example, would be B1, B2, B3, white would be W1, W2, W3, and W4, and T would be T denotes, let me see, let us denote blue balls by B1, B2, B3, and white balls by W1 through W4, then a sample space. Then the sample space of the experiment is, if you get heads, you get basically all the balls, and if you get tails, okay. So the sample space would be something like this. The sample space would be basically if you toss the coin, was it a coin? If you toss the coin, and if you get heads, then you draw a ball from these balls, which is basically 3 blue balls and 4 white balls. So that would be for example, HB1, HB2, HB3, HB3, and HB4. And then you could go for these white balls as well. So HW1, HW2, HW3, and HW4. And then if you get tails, then you throw a dice. So suppose that you get tails and throw dice, you get a 1, for example. You get tails, and throw dice, get a 2. Tails, throw the dice, you get a 3. Tails, you get a 4. Tails, you get a 5. Tails, you get a 5. And let me write this properly. Tails, you get a 5, and tails, you get a 6. That would be your sample space. So here by HB of I means head on the coin and balls, B of I is drawn, and HWI means head on the coin and the ball W of I is drawn. Similar, TI means tails on the coin and the number I on the dice. Okay, so that's clear. There is no problem with that. You just need to write it in such a way that, and you need to write down basically what your assumptions were. For example, H denotes heads, T, for example, denotes tails, and so on and so forth. So the next thing that we have, the next example is, consider the experiment in which a coin is tossed repeatedly until a head comes up. Describe the sample space. So you keep tossing a coin and repeatedly until heads comes up. So that means that you could, meaning that you could get basically your sample space would be either you toss the coin and directly and you will get heads. So then there your experiment is done. Suppose you get tails and then again you toss and you get heads, and there you have to stop. Suppose you get, for example, tails and another tails and then you get heads, and then you're done. Suppose you get tails and again you get tails and again you get tails, but then after 3 tries you get heads and you're done. Suppose you get tails, 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 and again tails, and again another head, and so on and so forth. Okay, so that's basically the kind of thing that you can expect to learn here. And this is basically the last chapter of class 11 of the book related to class 11. This is, of course, probability. And let me see if we have mathematics class 12. Let me see what we have here. So in class 12 we have, as you know, class 12 is basically 2 books, 2 parts. So you have relations and functions, and determinants and continuity, application of derivatives. So over here we don't have any probability anymore in part 1 of this book, and part 2 PS, and over here we have basically one more chapter in class 12 related to probability as well. Okay, so in the next video we will talk about exercise 16.1. I'll see you in the next video.